students, today we will study about current electricity. So let us begin it with what is current electricity. That means we are having some charges and these charges are in motion. That means these charges are moving. They are not stationary, because when the charges are stationary, then we categorize them into electrostatics. Now the second step after electrostatics, we have done all the basics of the electrostatics, how the charges behave when the charges are stationary. That comes under electrostatics. And whatever is in electrostatic that we have done, and the link for all these lectures you can find below that I have given. So a step forward after electrostatics is when our charges are moving. Our charges are in motion. They are no more stationary. Then it comes under the category of current electricity. So we can now define that what is an electric current. So whenever our charges are in motion, the charges we are considering, they are moving. So charges in motion constitutes electric current. So the electric current we are talking about is nothing. It is only constituting of the charges which are moving. And these charges are not stationary, they are moving and they are in flow. Moving means the charges are flowing. The charges are in flow. For example, if we consider electron, then if there is electron flow, then we call it as current. And to represent this quantity current, we use the symbol small I. So whenever in the physics you see the symbol small I, it simply denotes electric current. And the charges are denoted, we are well familiar with that the charges are denoted with the symbol small q. So how come these charges are related to the current? Because the charges are stationary, we have done all the physics of it, we have done all the electrostatics, that is the basic. And once you are done with the basics, then you can quickly move to the current. So now our charges are not stationary, they are in moving position, they are in flow. So if they are in flow, then we can calculate the current. Then how can we calculate the current? For that, we should know that if there is an area and across that area the charges are flowing. So we consider the net amount of charges flowing across the area in the forward direction and these charges which are flowing through any area we have taken, if the time interval we have taken is a small t, so the charge flow is in the time interval small t. Then we define our current, which is represented with the symbol small I, is I is equal to Q upon T. Here I is the current, Q is the charge represented with the symbol small q, and T is the time. So very quickly we can say that if we have any area and the charges which are flowing through the area is a small q in the time interval small t, then we can easily calculate the electric current as simply divide the charge with the time interval. So the rate of flow of charge is current, and this gives us the definition of current. What is an electric current? The rate of. Whenever we say the rate of, that means we are considering it with the time, per unit time, because per unit time gives us the rate. So per unit time the flow of charge is current. So current is the rate of flow of charges. And the unit we use for the electric current is ampere. It is a very basic unit You are well familiar with this unit. You might have studied it in your 11th class or maybe in your 10th class. So that is in the very basic school when we study the basic units, then we get the ampere. But for now you have to just remember that ampere is the unit for the electric current. Whenever we calculate this electric current small I, it is represented with the unit ampere, and this ampere is also a very larger unit, so we sometimes represent it in milliampere or in microampere. So whenever you see a milliampere, that shows 10 to the power minus 3 ampere, or a microampere corresponds to 10 to the power minus 6 ampere, and it shows the amount of current that is flowing through any of the conductor or any of the material we have chosen. So whenever you need to calculate the current, you can simply use the formula I is equal to Q upon T and use the unit as ampere. But this is not always the case. All the time you always need not calculate this current. Sometimes you are asked in the numericals to calculate a different type of current. Maybe it may be an instantaneous current. Instantaneous current means at the same instant. Instantaneous current. Now let us understand this term instantaneous. So what instantaneous corresponds to? Instantaneous means at that instant. We are talking about a particular instant at that time. At say t is equal to 2 seconds, or t is equal to 5 seconds, or t is equal to 10 seconds, or t is equal to 12 seconds. So at that instant, whatever time we are given, that is the instant. And if we need to calculate the current at a particular time, at a particular instant, then this current is termed as instantaneous current. So if you need to calculate the instantaneous current, that is the current I at a particular time t, then you can calculate it simply by differentiating this charge q with respect to t. So the instantaneous current always comes out to be by differentiating q with respect to t. So that you have to remember, because at any instant, so we have to differentiate because we have to get a particular value, and this formula will give you a particular value. Second thing that we come to is the average current. Now what is this average current? Suppose you are starting a medium and you are calculating the current that is flowing through that medium, and that current is varying. This current is changing with time. That means the current is not constant. So if you are given with any time interval, so within that particular time interval, the current is varying. It may be increasing, it may be decreasing, or sometimes it is constant then decreasing or constant then increasing, but it is not constant throughout the time interval. Then what we do? Then we calculate the average current, that is the average of the total current, increasing, decreasing, constant. Then we have to calculate the average of that current. So whenever you need to calculate the average of the current, then we write down the current I, the electric current. So this is the variation in the charge with respect to the variation in the time. This delta always symbolize variation or the change. So if there is a change in the time interval, say the final charge will be Q2, initial maybe Q1. So this is Q2 minus Q1, and the time interval is T2 minus T1. So whenever you have to take the average, that means you have to take the change in the charge and the change in the time. So that is Q2 minus Q1 and T2 minus T1. Then you are given with some time interval. Then you have to put on the value of the change in the charges and the change in the time, and then you will get the average of the current. You can put a suffix average here. So this will give us the average current. So the simple formula we can always use is, that is the default for a current I is equal to Q upon T. If at any instant, then it is a function of t, then you can simply differentiate. If you want to calculate the average, then you have to simply take the variation, the change in the charge and the change in the time. So these are the three formulas that may solve all of your board or NEET or competitive exams. Whenever you are using this current, then most of these are solved. The current calculation is solved by these three simple formulas. Now let us come to the two types of current. If I take this current I, it is a function of t, and this is the variation in the charge with respect to the variation in the time, or the change in the charge divided with the change in the time. And if we take this limit delta t tends to 0, Okay, then we call this as non-steady current. Non-steady current means the current is not steady with time. The current is varying. So whenever you use non-steady current, then you have to use this variation in charge, variation in time, and the limit delta t tends to 0. And if you are having any steady current, so for all the steady currents, our standard formula will work. This holds true for all the steady currents. Steady currents means the currents which are not varying with time. So hope you got the thing. If our current is varying with the time, then you have to simply take the variation charge, variation in time, and take the limit delta t tends to 0. Then it gives you the formula for non-steady current. Current which is not steady with time, which is not constant with time, it is varying. And if you are giving the value of the steady current, then the current is constant. Then we can simply use I is equal to Q upon T. And this comes under the electricity, and whenever our charge is accelerating, then we have to move to the next branch, that is electromagnetics. But we will study in the later chapters. Right now, we will limit our studies in this unit. We will limit our studies to only electricity. So whenever we are studying about current, that means we are studying about some charge carriers, right? Because there is a flow of charge, there is carrying away of these charge. And whenever we talk in terms of metallic conductors, then for these conductors, the charges that are flowing are basically electrons. So for metallic conductors, electricity is always talked in terms of the flow of electrons, that is the negative charge particles. So how there is a flow of current, how there is a charge flow within the conductors. So what happens if we are talking about the solid conductors? So how the current is flowed through a solid conductors? Current is simply carried by these negatively charged electrons, which we call as negatively charged particles. So these electrons, they are the charge carriers, and we term these electrons as free electron, or if you go to the higher classes, we can call them in terms of the electron gas, because there is a huge density of these free electrons. So sometimes these are termed as electron gas, but as for now you can only consider that these are the free electrons. So within the solid conductors, these free electrons are present, and these are the charge carriers, so they carry the current. And whenever these electrons, they leave any neutral atom, then what is remaining behind is always the positive ions. So in the background we have all the positive ions, and what is moving, what is carrying the current is always electrons. So we can say that for the solid conductors, current is basically carried by these negatively charged electrons, and this is in the background of fixed positive ions. Now if we're talking about current in conductors, then a very important law to remember is Ohm's law. If we have done with the basic physics, then we are familiar with Ohm's law. But let's quickly revise what is this Ohm's law. So to understand the Ohm's law, we first consider any conductor, because conductors are very good in flowing the current. Their resistivity is minimum. They have a low resistance value to offer to the flow of current. So that is why Ohm's law has very importance, and it is a very important law whenever you are studying electricity. So what is this Ohm's law? That if we have a conductor, and through this conductor if the current I is flowing. I repeat, we have a conductor, and through this conductor a current I is flowing. And this current I is flowing due to a potential difference V. So V is the voltage we have applied, and due to this potential difference between the two ends of the conductor, if the current which is flowing is I, then the voltage is directly proportional to the current that is flowing through the conductor. Now if you want to remove this proportionality sign, then we have to put a constant, and if we say that if I remove this proportionality sign and I write it down as V is equal to, if I introduce a constant, that is say R. So this R is a constant, then this V is equal to IR is the Ohm's law. If I write it down in the caps form, then this is the voltage developed, I is the current, and R is the resistance. So this is always the expression we have to remember for Ohm's law. V is equal to IR. And what is the statement of Ohm's law? that if we have a conductor through which current I is flowing and V is the potential difference between the end of the conductors, then according to Ohm's law, this V is directly proportional to the current I, and if we remove this proportionality sign, then we introduce a constant which is capital R, and this gives us with a very important formula V is equal to IR. So R here is a constant of proportionality, and this is the resistance of the conductor. R is the resistance which is offered to the flow of these electrons or to the flow of current. R is the resistance offered. And this resistance is offered within the conductor itself, right? It is constant for a particular thing. It is constant here. R is a constant which we call as resistance, and this is the resistance offered by the conductor, and the unit of this resistance is ohm, and the symbol we use for ohm is this. This is the symbol of ohm. So whenever you are representing any resistance, use the symbol R, and the unit is ohm. Resistance is always measured in ohm. Now, what are the factors that decide the resistance of a conductor? So let's quickly find out that what are the factors. This resistance of any conductor depends on the length of the conductor. It is directly proportional to the length of the conductor. That means more the length we are having, more the resistance we will be getting to the current. More the length we are having, more the resistance will be offered to the flow of current. And it is inversely proportional to the cross section of that conductor. That means if we are having a high cross sectional, that means the resistance offered will be low. So again, to remove these two proportionality sign, we have to put an equal to sign. Then we introduce a constant. This is rho L upon A. We have combined these two because resistance is directly proportional to length and inversely proportional to the cross section. So remove these two proportionality sign, put a constant rho. Here this is a rho. This is a symbol of rho, and this is known as resistivity. This is also known as specific resistance. So don't ever get confused with what is the difference between the resistivity and specific resistance. So resistivity and specific resistance are the same thing. The resistivity of a metallic conductor has a constant value. The specific resistance also have a constant value. It depends on certain factors that we'll study, but it has a constant value for a particular conductor. And this resistance R, this does not have a constant value. It depends on the length of the conductor. For example, if you take 1 meter of a conducting wire, then you calculate the resistance R, and if you just double the length, you make it 2 meter and then you calculate the resistance. So obviously the 2 meter long conducting wire will be offering more resistance in comparison to a 1 meter long wire. So the resistance of any conductor varies with its length, and it also depends on its cross-sectional area. And next we go to is say the cross-sectional area. If we are having a conducting wire, then the cross-section will be whose area is given as pi r square. So pi has a constant value. So for this value, say for the cross-sectional area A1, I'm having the resistance is R. Now if I make this radius as double, just remember, like we have double the length here, here I am doubling this resistance. So this new radius is 2 times of the previous radius. Then see what will be the new cross section area. It will be simply pi r dash square. That means pi, and this r dash is twice of initial value r. So this comes out to be 4 pi r square. That means our cross sectional area A2 will be 4 times of the initial value. Then if I say that the resistance R will be having the value of rho L upon pi r square, and our new resistance R dash will be having the value of rho, length the same, and this is 4 pi r square. So you can see this R dash will be 1/4 of the initial value. That means if I have increased the cross-sectional area, then the resistance value becomes 1/4. So this resistance, it directly depends on the length in the cross-sectional area. So you cannot have a fixed value. It does not only depend on the material of the conductor or temperature only, because if a 1 meter length wire obviously will be having less resistance than a 2 meter length wire. If you go on increasing the length, the corresponding resistance will increase. See, a bundle of wire and only a 1 meter of wire, they both will have a different resistance in spite of being of the same material at the same temperature. So the resistance is always a varying quantity, but resistance, if it is specific resistance or if this is resistivity, then it is constant for a particular material. It only depends on the material of that conductor and also on the temperature. So mind this thing it should be always in your tips that resistance is always a variable quantity. It never has a fixed value. It varies according to the length, cross section, all these things. But specific resistance or resistivity is kept fixed. It is decided with the material and it depends on the temperature. How you can have a direct relation between the resistance and the resistivity, right? R is equal to rho L upon A. This is again a very important formula. R is equal to rho L over A, or rho is equal to RA upon L. Now we know that the unit of resistance is in ohm. Then if you want to calculate the unit of specific resistance or resistivity, then you can do it very easily. How come? So since R is equal to rho L upon A, we know the unit of this, we know the unit of this and this. This resistance, it is in ohm, length is in meter, area is in meter square. So if we calculate rho comes out to be RA upon L. Resistance is in ohm always. Area is maybe in meter square and length is in meter. So this is simply ohm into meter. So specific resistance is ohm into meter or ohm meter. So what is the unit of specific resistance or resistivity? It is ohm meter. So this value of resistivity depends on the type of, because a copper or a gold or a silver, they may have a different specific resistance or different resistivity. So resistivity is in general constant for type of a material that is offered to the flow of current. And just inverse to the resistivity is conductivity. So if you do 1 upon rho, if you inverse the resistivity, then you will get the conductivity. And if you are talking in terms of metallic conductors, then conductivity is high and the resistivity is low. That is why they are very good conductor. Whenever you talk about very good conductor, that means it is conducting high and resisting low. Resistivity is low, conductivity is high. And whenever you are talking about any of the insulator or the metal or any material which is less conducting, then the conductivity is low and the resistivity is high. So these two are inversely proportional. High conductivity, low resistivity. Low conductivity, high resistivity. So sigma is equal to 1 upon rho. If you know the conductivity, then you can also calculate the resistivity. Or inversely, if the resistivity is known to you, then you can easily calculate the conductivity of that particular material. So that was only the one form of Ohm's law. Now let's go quickly to the second form of Ohm's law. And for that we have to define a very important quantity, that is current density. Current density, and the symbol for current density is J, capital J. Sometimes you may get small j also, but usually it is represented with the symbol capital J. So this is a current density. Current density means simply take the current and divide it with the area, because current is always flowing through some area. As just now we studied that if there is a current flowing through some area, then we calculate the net amount of current, then we find out what is the average current, what is the instantaneous current, if it is a steady current or if it is a non-steady current. So if you simply divide this current with the area, then you will have the current density. So J here corresponds to current density. And what will the unit? It is very simple, because this current I we are always having in amperes and this area A will be in meter square. So current density J will have the unit of ampere per meter square. How much amount of current is flowing through a unit area or how much amount of current is flowing through 1 meter square. That simply gives us the current density, and it has a symbol J. So what was our Ohm's law? Ohm's law was simply V is equal to IR. V is the potential developed across the ends of the conductor. I was the current that we have represented for this law. We have taken capital I, and R is the resistance offered. And if we talk in terms of the electric field which is developed into the conductor, then the voltage developed will be the electric field, and say if L is the length of the conductor, then volt is the electric field multiplied with the length. That is a very simple formula. We have done with it. If you want to know, then you can quickly go to the lectures where we have discussed this potential and the electric field. Then V is equal to E into L. So instead of V, we can write down EL. We can simply use this value over here. So substituting V in this formula, what we get? E multiplied L, that will give us the voltage V is equal to I is the current, and R we want to write down in terms of resistivity. So what is the value of R? R is equal to rho L upon A. Simply put the value I multiplied with rho L upon A. This is the value of resistance R. So we will have this is I upon A multiplied with rho multiplied with L. And I upon A is simply our current density. So this will be written as current density J. This is resistivity and this is length. So what we have? E multiplied with L is equal to I upon A is the current density. Then rho is the resistivity and length. So L cancels out from both the sides, and we have this equation as E is equal to J rho. Or if you calculate the current density J, it comes out to be 1 upon rho multiplied with the electric field E. What is 1 upon rho? The inverse of resistivity is always conductivity. So this J is equal to sigma is our second form of Ohm's law. So what is Ohm's law? Either you can write it as V is equal to IR, or you can write it down as J is equal to sigma E. Now we know all the values of these. This is voltage, this is current, this is resistance, this is the current density, which is I upon A, current per unit area. This is our conductivity, high conductivity, low resistivity, high conductivity. Conductivity is high for conductors, and E is our electric field. So just remember, V is equal to IR and J is equal to sigma E. Both of these are Ohm's law. These are the two statements of Ohm's law, or two formula corresponding to this statement of Ohm's law. Now here I have said that this current density is a vector quantity and electric field, as we know, is a vector quantity, and the sigma is obviously a scalar quantity. So if this current density is a vector quantity, what about the current I? Is it a vector quantity or a scalar quantity? So V is equal to IR is the scalar form and J is equal to sigma is the vector form. Although I is a vector, but we consider it as a scalar and it does not follow the property. Now come to the most important topic, drift velocity. So what is the drift velocity? It is a type of velocity through which electrons are drifted. First we go through it and then I'll make you clear why is it called a drift velocity. So in order to understand this, we have simply taken any conductor. As you can see that this is a conductor here and this is the length of the conductor. The length we have denoted with delta x, because there is a flow of electrons, there is a flow of charge. So if they are flowing, then the total distance they have to cover is delta x. And because we will be calculating the resistivity and everything, so we have taken this conductor which is having a cross-sectional area A. So A is the cross-section and delta x is the length of the conductor. So first of all, if we are having any conductor, that means we are having some free electrons. That is the basic characteristic of any of the conductors. There are some number of loosely bound electrons that we call as free electrons. So if it is a conductor, it is having a number of free electrons and there is no field present. Initially we are taking that there is no electric field. First we will do it in the absence of electric field. So we are considering here that there is no electric field. So these free electrons, they are moving within the conductor. There is a motion of these free electrons, And during this motion, these free electrons, they are colliding with the fixed heavy ions. Suppose there is a neutral atom, then electron is out of it, then this is what is remaining is a positive ion. So whenever these free electrons are moving, they continuously collide with these fixed heavy ions. Okay, so whenever they collide, the free electrons have a collision with these fixed free ions, then again they emerge out with the same speed. But what happens when this electron is moving, then it is colliding, then there is no directing force. Just pay attention that there is no directing force. They are moving randomly, then they are colliding, then their direction is changed, and then they move here and there. This is an electron moving, then this collides, then its direction is changed like this, then this may come out like this, or this may be this. So this is always in the random direction. The collision between the fixed free ions and the randomly moving electrons, these are free electrons, it is having the same speed, but the direction is random, right? So we can say that the speed is not zero because speed does not consider the direction, the magnitude. So the speed is remaining the same, but the velocity, the average velocity is zero. So if we take that the velocity of electron as Vi, then see, if we take the average, this summation is taken between, say there are n collisions, so from I is equal to 1 to n. This I is not current here, it corresponds to the velocity of any of the ith electron. So this is the velocity corresponding to the ith electron. So there are electrons from 1 to n. So we have considered n number of electrons. So their average velocity, average, we take the average, if we take the total velocity and if we divide with the number of electrons. So the number of electrons is n. So if we divide this total velocity with the number of electrons, then we have the average velocity. So the average velocity of all these number of free electrons which are moving within the conductor, then this average velocity comes out to be 0, right? That means all the free electrons, they are moving, but since they are moving in the random direction, so their net or average velocity comes out to be 0. Now next what we do is, we apply any electric field to it. So let us say that within this conductor, so whenever we apply an electric field, there is an internal electric field developed into the conductor and the electrons are directed in the direction opposite to that of the current. We are applying an electric field. So let us say this electric field is maybe in this direction you can take. This is the direction of electric field. Okay, so within this conductor we have applied the electric field E. Now when the electric field comes into the picture, that means there is a driving force. Initially the electrons were moving randomly, but there is now a directing force. What is the directing force? This electric field is creating the directing force. So all these electrons which are free electrons, they are accelerated. All these free electrons, these are accelerated due to electric force. And this electric force is due to the electric field we have applied. That means all the electrons which are present inside this conductor, they will experience a force. Which force is this? This is the force due to electric field or the electric force, right? So because electrons are negatively charged particles, so they will experience the electric force of E into E. Here E is the charge on the electron and this is the electric field. So this is the electric force that is applied on the electrons. And what is the general formula to calculate the force? Force is always mass into acceleration. Here if we talk in terms of electrons, then the force which is working on the electrons is equal to the mass of electron and the acceleration of electrons. So this is the electric force and this is the general formula of the force. So we can equate these two. So from here we can say that if we calculate this force, electric force, it is equal to a general formula of force F is equal to ma, then we get the acceleration of electrons with what amount they are accelerated, then this will be minus E upon m. So this is the acceleration which is working on the electrons. And if we know the acceleration, then we can easily calculate the speed or the velocity. And if we know the acceleration, then we can calculate the velocity. The velocity we have taken for electron is Vi. I corresponds to any of the electron, which may be 1 to n. So the velocity at the time we have taken is t. So the velocity at time t will be, since we know the formula that acceleration is velocity upon time. So if you want to calculate the velocity, you simply multiply the acceleration with time. So acceleration, we have the value. So we have this velocity is equal to acceleration multiplied with the time. So at any time t, any of the electron will have the velocity minus E upon m into t. Okay, because this corresponds to any of the electron. So this is for any of the electron. And if you want to calculate the average velocity at any time t, then we have to take the average velocity of all the corresponding electrons. So see, if these electrons are moving, then there is a collisions, there are successive collisions, then there is obviously some time interval between these successive collisions. An electron is moving, it is moving, have experienced the force, it is moving with this acceleration, then all of a sudden it collides. Collides means it comes to rest, then again it starts moving, then it collides. So between different successive collisions, there is some time. So if we represent this time between the collisions, then this is known as relaxation time. That is the relaxation between the collisions. So tau is always the relaxation time. That is the time between the two successive collision of any electron. So that is relaxation time. Then we can define the drift velocity. Drift velocity is the velocity of electron. Then first of all, we take the average velocity of all the electrons plus now we have taken this velocity. So this is, put the value of this velocity, and here we have to replace this time with the relaxation time, because this velocity depends on the relaxation. The time for which it is relaxed, then only we can have this velocity. The time between the successive collision will only hold this velocity, because when it is colliding, the velocity will become 0. So that is true only for the relaxation time. So we replace this Ti with tau. Tau is the relaxation time. So the average velocity when there was no electric field, it is 0. Minus when we apply the electric field, this is the velocity. So we get the formula for drift velocity as minus E upon m into tau. V is the drift velocity, the velocity with which the electrons are drifted due to the presence of electric field. E is the charge on electron, E is the applied, capital E is the applied electric field, m is the mass of electron, that is 9.1 into 10 to the power minus 31 kilogram, and tau is the relaxation time. Then how much is the relaxation time? It is of the order of 10 to the power minus 14 seconds. So this is the formula we get for drift velocity. So whenever you want to do the derivation or you want to do certain numericals, you can do this. Now what is the direction of flow of electrons? If you come to this diagram, then this electrons, they will always flow in the opposite direction to the electric field. So all those electrons, they will be flowing in the reverse direction of this electric field. Say these are the electrons, then this will be the direction of their flow. Now the next thing is that we want to calculate the conductivity corresponding to this conductor. So it is also very easy to calculate the conductivity. So let us say this, we consider this conductor again, where we are having this cross-sectional area as A and the electric field is applied to it. And let us say that the number of free electrons with this conductor is small n. So small n is the number of free electrons that we are considering within this conductor. So these are the number of free electrons per unit volume. That means in a unit volume of this conductor, the number of electrons present, number of free electrons present is small n. So number of free electrons per unit volume is small n. And the charge on each electron is this. And the charge on each electron is E. So let us say that these electrons, they are moving towards and they are crossing to this cross-sectional area A. So what is the number of these electrons which are passing through this volume? The number of electrons per unit volume is small n and the charge is small e. And if you calculate the volume, because this is the number is per unit volume, so if you multiply it with the volume, you will have the total number of electrons. So volume is, this is cross-sectional area A, and if you multiply it with the length delta x, then you will have the total volume of this conductor. Right? Volume is cross-section area and it is multiplied with the length. So if you continue this cross-sectional area up to the whole length of the conductor, you will have this conductor. So that is the total volume of this conductor. And if you want to calculate this length, then it is very easy to calculate because the electrons are now moving with the drift velocity Vd. So the velocity of these electrons is Vd, and the time we can take is, say, that we consider that the total electrons or the charge transported across area A to the right in delta t time. So in the delta t times, electrons are drift with the velocity Vd, then the distance covered delta x will be velocity multiplied with time. So we can say that the length will be Vd delta t, right? So the volume will be A multiplied with Vd delta t. So the total volume comes out to be A Vd delta t. So if you multiply this n with A Vd delta t, then you will have the total number of electrons and the charge on each electron is minus e. So this is the total charge. So total number of electrons. The number of electrons, this is the number of electrons per unit volume. So we multiplied with the volume. So this is the total number of electrons, and this total number of electrons each having the charge E. So this will give us the total charge carriers. And the total charge carriers can also be calculated with the formula, because we know that I is equal to Q upon delta T. So we can calculate the charge with the current multiplied with the interval delta T. So the charge is electron here. So the total electrons will be the total current flowing in the time delta T. So this is the expression for total charge within the conductor, and this is also the expression for the total charge in the conductor. This is in terms of the number of electrons multiplied with E, and this is in terms of the current multiplied with time delta T. So this is the total charge in the conductor, and this is also the total charge in the conductor. So we can equate these two. So as we see that delta T is present in both the terms, so that will cancel out, and it gives us I is equal to an EA Vd delta T. It may be written in this form. Here we have neglected this because minus only represents that the direction of flow of current is exactly opposite to the direction of flow of current. So minus denotes the direction only. So for now, we can neglect this because minus only represents the direction. Now we know the value of Vd. We have just calculated the drift velocity. Put the value of drift velocity. The value of drift velocity is, it is NEA. The drift velocity is having the value of EE upon M to tau. And this is multiplied with delta T. So simply put the value of drift velocity. So on equating these two, we have the current I as NEA Vd This is in terms of the current and this is in terms of the total charge. This is the charge in single electron multiplied with the total number of electrons. So if we compare these two, we have the current as NEAVD. Now we simply substitute the value of drift velocity as we have just calculated the drift velocity. A and the value is E upon m, and this is multiplied with the relaxation time, the time between two successive collisions. Make it a note that twice the relaxation time between two successive collisions. So that is the expression we have for the current. Or this may be written as the current I is equal to and E, then in the bracket we have E upon m into tau, and this is multiplied with A. And again, if we take A here, this side, then I upon A will give us the current density, that is the current per unit area, that gives us the J current density. So the current density comes out to be an E square upon m into tau E. Now simply use the Ohm's law. What is the Ohm's law? That V is equal to IR, or the second is in terms of current density, J is equal to sigma E. So if you compare these two equations, this is J is equal to this value into E, and the Ohm's law is J is equal to sigma E. So all this value corresponds to the conductivity of the conductor we are taking. So in comparing with the Ohm's law, we have the conductivity sigma as n E square upon m into tau. So we have the conductivity sigma as n E square upon m into tau here. N is the number of electrons per unit volume, E is the charge on electron, m is the mass of electron, and tau is the relaxation time, that is the time between two successive collisions. So this is again a very important formula if you go to the numericals, either maybe any of your competitive exam, even for IIT, JEE or NEET, you will definitely have numerical based on drift velocity or on conductivity. So if the concept is very much clear to you that whenever we are not applying any electric field, then also the electrons are moving, free electrons are moving, and they are colliding with all those present fixed positive ions. So they are colliding with that, and in that case they are moving in the random direction. So the average velocity comes out to be 0. Whenever we apply an electric field, then they are drifted in the direction opposite. Here you can see that they are drifted in the direction opposite to that. Then they are drifted in the direction opposite to that, and then we calculate that tau is the relaxation time. So then we calculate the expression for drift velocity, and once we know the expression for drift velocity, then we can calculate that there are how many charges which are moving, which are crossing its cross-section area. So this per unit volume is small n, then we are multiplied with the volume of this conductor, and then we get the total charges. Then we can calculate the total charges in terms of the current, and then we get the expression for conductivity. Now there is one important thing, that this electric field here, you can see this electric field I have shown that it is developed inside the conductor. See? This electric field is developed inside the conductor, because when there is no electric field, then the electric field inside the conductor is always 0. But whenever there is an electric field is applied, whenever the current is applied, then these electrons are drifted. So whenever there is no drift force, there is no driving force for the electron, then the electric field inside the conductor is 0. But whenever there is a driving force which is applied to the ends of the conductor, then these electrons are always drifted, and the electric field inside the conductor is not 0. Another important term corresponding to the drift velocity is mobility. We know the conductivity, we know the resistivity, and we should also know what is mobility. This mobility is the magnitude of drift velocity per unit electric field. So we know the drift velocity This is represented with the symbol V suffix D, and if the magnitude of this drift velocity is divided with the electric field, then what we have is the mobility. So this mobility is the magnitude of drift velocity per unit electric field. And this shows the mobility of the charge carriers, how they are moving. If their drift velocity is high, then obviously they will be having high mobility, and if the electric field is low and they are moving, so it is inversely related to the electric field. Higher the electric field, the mobility will be less, and the lower the electric field, then mobility should be high. So this inversely related to the electric field and directly related to the drift velocity. If you want to calculate the unit of mobility, then it is very simple, because here we have the drift velocity, and drift velocity will be in meter per second, since this is the velocity, and the electric field is in volt into meter. So this is again volt per meter. So this is again volt into meter. So the unit comes out to be meter square upon volt into second, right? So this is the unit of mobility. And the practical unit, because practically this meter is very high distance to travel, so for the practical unit it has centimeter in place of this meter. So the practical unit is centimeter square upon voltage into second, and it is of the order of 10 to the power 4 centimeter square per volt into second. That is the practical value of mobility. And this mobility is always positive. Mind this thing, that the mobility of charge carriers, or in case we are considering the mobility of electrons, is always positive. Mobility of charge carriers is always positive, because it shows how they are moving, and this mobility or the moving, it cannot be negative in any sense. So now we know the velocity of the moving electrons is called the drift velocity, and it has the magnitude of E upon m into tau. So if we put this magnitude of drift velocity in the formula, mu is equal to the magnitude of drift velocity divided with the electric field E, then we may have the formula as mu is equal to, put the value, it is E upon m multiplied with tau to E. So this electric field E cancels out, and this comes out to be E tau upon m. So the formula of mobility, mu, is E tau upon m. This is again very important, a formula if you want to calculate the mobility of free charge carriers, mobility of free electrons. Then simply the charge on electron multiplied with the relaxation time divided with the mass of the electrons. You have to simply remember that mobility is drift velocity. If you divide the drift velocity with the electric field, you will have the mobility.
So that's all for now. If you like this lecture, then like and share and subscribe to our channel Physics Class, so that you receive notifications for more such lectures. Thank you.